Welcome back, Focus Learners. I am incredibly excited to have you join me for today's explainer. We are diving into a massive, frankly mind-bending topic today. We're talking about how the global semiconductor industry is literally smashing right through the physical limits of traditional computing. Seriously, it's a complete reinvention of the technology that powers our entire modern world. So get comfortable, focus in, and let's explore exactly how we are breaking the silicon wall.
So think about this for a second. How exactly do we build the future of technology when we have fundamentally hit the physical limits of silicon? I mean, for decades, Moore's law told us we could just keep shrinking transistors down to pack more power into our chips. But physics has finally caught up with us. We are at a threshold. And to understand how we push past it, we've got to look at the groundbreaking solutions that are emerging right now.
Here is our roadmap for this explainer. 1. The silicon physical limit. 2. Atom beams replace light. 3. Agentic AI chip design. 4. Post-silicon hybrid materials. And finally, 5. The next computing era.
Okay, let's dive into Section 1, the silicon physical limit hitting the wall.
You'll hear industry insiders call this absolute threshold the silicon wall. Basically, traditional chip manufacturing relies on EUV, extreme ultraviolet light, to etch patterns onto silicon wafers. But as we try to make features smaller and smaller, the wavelengths of light simply aren't fine enough anymore. It's kind of like trying to paint a highly detailed microscopic portrait using a thick, clumsy house painting brush. It just doesn't work. Heat becomes unmanageable, energy consumption spikes, and efficiency plummets. We need an entirely new toolkit to break through this wall.
Moving right along to Section 2, atom beams replace light. This is Pillar 1, how we print them.
So traditionally, the industry standard relies on extreme ultraviolet or EUV light, utilized by giants like ASML. But now, we have what's being called beyond EUV or BEUV. Lace Lithography, which is this really fascinating Norwegian startup, is pioneering this space by using highly precise beams of helium atoms instead of light. Going back to our analogy from before, if EUV is a thick paintbrush, Lace Lithography's helium atom beam is a microscopic atomic needle. It is a fundamental shift from optics over to particle physics.
And get this, the industry is taking this very, very seriously. Lace Lithography just recently raised a massive $40 million Series A funding round. What's absolutely crucial here is who is backing them. We're talking major players, including Atomico and Microsoft's venture fund M12. When you see capital of this magnitude flowing from major tech stakeholders into atomic-level lithography, it proves there's serious industry belief that light-based printing is reaching its end, and atoms are the actual future.
The sheer scale of this performance upgrade is just staggering. By using helium atom beams, Lace Lithography aims to enable chip features up to 10 times smaller than the absolute limits of current EUV technology. We are literally pushing manufacturing toward true atomic scale precision. And this mind-boggling scale isn't just for bragging rights, right? It is absolutely essential to support the massive future demands of advanced artificial intelligence, photonics, and quantum computing.
Professor Bodil Holst, the co-founder of Lace Lithography, summed it up perfectly. She said, "Our technology is a way that can potentially expand the roadmap and be an enabler for doing things that would not have been possible otherwise." I love this quote because it forces us to zoom out. Printing chips with atoms isn't just some minor incremental upgrade. It's an entirely new paradigm for hardware that unlocks capabilities we haven't even dreamed up yet.
All right, Section 3, Agentic AI chip design. Pillar 2, how we design them.
Now, what's really interesting here is how Samsung utilizes a multi-agent workflow for this exact challenge. This is not just a single AI helper, it's practically a collaborative intelligent assembly line of AI architects. In step 1, a specialized schematic agent predicts performance, power, and area before any layout is even generated. Then, in step 2, a layout agent autonomously refines the design in response to those schematic updates. Finally, in step 3, real manufacturing insights, like wafer-level pattern data, are fed directly back into the early stages. It's this continuous autonomous loop of optimization.
The impact of this? Absolutely huge. By incorporating this agentic AI workflow, using reinforcement learning and genetic algorithms to automate complex analog and logic designs, Samsung has slashed its design turnaround time by roughly 50%. 50%. For cutting-edge, AI-optimized memory products like HBM4, cutting the design cycle in half is a colossal competitive advantage.
And the brilliance extends right out of the design lab and directly onto the factory floor.
Samsung has actually recreated a full-scale semiconductor fab as a digital twin built right on the NVIDIA Omniverse platform. By feeding real-time manufacturing data into this virtual replica, AI agents can detect anomalies, perform predictive risk assessments, and trigger proactive interventions instantly. It's system-level optimization from the very first sketch all the way to the final factory output.
Section 4. Post-silicon hybrid materials. Pillar 3. What we make them from.
To explore this next pillar, one of our sources includes a rather unique perspective from an Arabic text that utilizes al-Jafr, which is a traditional numerology forecasting method. Impartially speaking, what is so fascinating here is that this source uses this traditional forecasting to project highly specific, advanced material science outputs. It predicts a necessary transition toward ultra-wide bandgap hybrid materials to overcome the heat and speed limitations of our current silicon generation.
There are 3 exotic materials highlighted in this research. First up, gallium. It acts as the key, offering extreme speed and, in liquid metal alloys, really unique flexibility and self-healing properties. Second, diamond. Referred to as solid light, synthetic diamond provides unmatched heat dissipation. It can handle incredibly high voltages without melting. And finally, boron nitride. Acting as the shield, it's an ideal insulator that allows these extreme materials to be integrated together smoothly. Each of these solves a distinct, critical bottleneck of current silicon.
So the crucial point here is the Guy-Diamond-BN heterostructure. It's a mouthful, I know, but by layering gallium, diamond, and boron nitride together, researchers are predicting the creation of the ultimate post-silicon canvas. It combines the massive power capacity of diamond, the lightning speed of gallium, and the protective isolation of boron nitride. This allows us to build devices that are fractions of their current size while running significantly cooler.
Now, you might be wondering, wait, isn't building computer chips out of diamond incredibly expensive? The sources actually offer a specific fabrication insight to solve this. The research suggests converting cheap, abundant carbon directly into synthetic diamond. By using gallium as a catalyst during this high-pressure process and adding trace amounts of gold to finalize the electrical conductivity and stability, these incredibly exotic diamond-based chips could actually be made commercially viable at scale. No way, right? But it's true.
And finally, Section 5. The next computing era, synthesizing the triad. Let's take a look at the timeline of convergence here. In 2026, we acknowledge hitting the absolute physical scaling limits of silicon. By 2028, multi-agent AI, like Samsung's workflow, becomes the standard to autonomously handle unimaginably complex designs. By 2029, lace lithography is slated to deploy its pilot helium atom beam tool in a working fab. And moving into the 2030s, these diamond and gallium heterostructures will scale commercially, acting as the foundation for this new hardware. All these separate tracks are hurtling toward each other over the next decade.
Let's zoom out one final time to look at why this triad of innovation matters to you, to consumers, to investors, and honestly, to our planet. Breaking the silicon wall unlocks next-generation AI capabilities that are currently starved for computing power. It will drastically reduce the physical footprint of our devices. Just imagine data centers shrinking by 80%. And crucially, by using materials like diamond that dissipate heat naturally, it delivers massive global energy savings, practically eliminating the need for the massive power-hungry cooling systems we use today.
Which leaves us with this final, powerful thought. When our computer chips are designed autonomously by AI, when their circuits are printed with atomic precision using helium beams, and when they are physically built out of synthetic diamond, what will computing even look like next? We are standing on the edge of an incredible technological frontier. Thank you so much for joining me on this explainer, Focus Learners. Keep exploring, keep learning, and never stop questioning the limits of technology. See you next time.